Okay, we are going to talk about line integrals and where they come from. To start, I want to remind you of where integrals come from. These are the pictures that we've seen with integrals. This is a function, and we're trying to find the area under this curve from a to b. So we break a to b up into evenly spaced points, and we find a rectangle approximating the function on each of these intervals, subintervals. We add all that together. That's what we're looking at here. What we're summing is a height times a width, which is an area. We add up all of the areas, and that's approximately the value of the area under the curve. That sum is called a Riemann sum. And in the limit, as the number of rectangles goes to infinity, or as the width of the rectangle shrinks to 0, we get an integral. And that is the exact area under the curve. We want to look at something similar now for a line integral. Okay, here is a similar picture, but a different scenario. What we have now is a curve, and we're representing the curve as a vector-valued function with a parameter domain. So the curve goes from time equals a to time equals b. The vector here is the position vector, and as time increases, the position vector traces out this curve in the xy plane. We're going to think of the curve as being a wire with a variable density in kilograms per meter. And our task, we're not looking for an area under the curve anymore. We're looking for the total mass of the wire. If the density were a constant, if the density were not variable but were constant, 5 kilograms per meter, we would just multiply the density times the length of the wire, and that would give us the total mass. But with a variable density, it's not quite so simple. We need to use calculus, and the calculus we need to use is similar to the Riemann sum idea, where we need to take the problem and break it up into pieces that we can manage. So for pieces that we can manage, what we're going to do is we're going to take this a to b interval, and we break it up so that we have a T naught is A, and then T1, T2, T3, and T sub n can be B, and there will be a delta T spacing between each of the T endpoints of these T intervals, and that spacing will be uniform with delta T. Those T's will correspond to different points on this curve. These won't necessarily be evenly spaced, but the delta T values that lead us from one to the other will be evenly spaced. If I look at one of these points, say this one, this is going to be x of t sub k, comma y of t sub k. So we have now a partition where we've broken the curve up into these different pieces. And the question we're going to ask is, what is the mass on one piece? We'll break this down into a manageable chunk and say, let's take this piece right here. What is the mass of the wire over that one piece of the wire? Then the idea is going to be familiar to us. We're going to add up all of the masses of all the pieces to approximate the total mass. All right, so we're looking for the mass of one of these pieces. This highlighted piece up here, and the mass of that one piece is approximately going to be the length of that piece times the density of that piece, right? The density times the length will give us a mass. So let's zoom in at that piece. Here's going to be our kth segment of that line, and the kth segment looks like this. We're zooming in here. This is the point x sub or x of t sub k minus 1, y t sub k minus 1, and this will be x t sub k, y t sub k. And that's a zoom in on the one piece, on some general piece that we've decided to focus on. And if we notice, we can make a right triangle or a right angle here, and I can connect these with a straight line so that we do have a right triangle. Now looking at that right triangle, let's look at it in another color. Looking at that right triangle, Let's make the right triangle up here. Oh, let's make it in the color that shows up. This length is x t sub k minus x t sub k minus 1. And this is y t sub k minus y t sub k minus 1. Or I'm going to call it delta x and delta y for the sides of that triangle. And that makes the hypotenuse the square root of delta x squared plus delta y squared. Now that hypotenuse right here is an approximation of the length of this piece of the wire. So we'll go back. It's an approximation to this, the length of piece K. All right, we can use that, and we're almost there. Okay, so the length of piece K and the density. I'm going to write these in the opposite order. The density was given by F. So we have F of x tk, comma y tk. And we have the length, which is the square root of this delta x squared plus delta y squared. That's still an approximation because the actual density varies over our piece. It's not the same from one end of the piece to the other, but we're approximating it because it's just a little piece. So it's approximately a constant density. And then we do have this length, which was also an approximation of the length of the segment, but a good approximation, especially if the segment is very small. So that's why we have an approximation here. Now, both of these quantities will become exact, and that approximation becomes exact as delta t goes to 0. So just like with the Riemann sum, as we take a limit as delta t goes to 0, we get something closer and closer to exact. So there's a little bit of work now, and we will have the line integral. All right, so this is our approximate total mass. We've added up the approximation of the density times the length for each one of those little segments. And that gives us an approximate total mass. Now, just a little bit of a trick I want to show you. We take this piece, the delta x squared plus delta y squared, and we're going to write that like delta t squared times delta x squared over delta t squared plus delta t squared delta y squared over delta t squared. So we've just multiplied and divided each term by delta t squared. That's a bit of a trick. It's multiplying by 1. It doesn't change anything, but it does change the way things appear and how we can work with them. So I'm now going to factor that delta t squared out of both of those terms, and then it can come out of the square root as delta t. So we're left with delta x or delta t squared plus delta y over delta t squared on the inside of the square root. So rewriting the mass now, it's approximately the sum of f of x of t sub k, comma y of t sub k times the square root of delta x over delta t squared plus delta y over delta t squared times delta t. This is the biggest thing we've done so far this semester. But this is where the line integral comes from. Now, this is a Riemann sum. What do we do with Riemann sums? We take the limit as the number of intervals goes to infinity, and they become integrals. So we just take a limit as delta t goes to 0, and we get the exact mass is exactly equal to the integral from a to b of f of x sub t comma y sub t times the square root. The limit of these terms here as delta t goes to 0, that's the definition of the derivative. So this is x prime of t squared plus y prime of t squared, and then we have dt. That is how we defined a line integral. And so we see through this process of finding the total mass from a mass density along a wire, breaking it up into pieces, adding the effect of each piece together, we get a Riemann sum, which in a limit turns into an integral. This is how we have defined line integrals.